This is the lecture on interval estimation, the material in Chapter 8. I think I can cover all of this material in one reasonably brief lecture. What we're going to do is add a margin of error to our interval estimate. The purpose of adding this margin of error is to provide information about how close or how accurate our point estimate is. The wider the margin of error, the less certain we are about our point estimate. There are a number of factors that can lead to a larger margin of error. Chief among them is sample size. So all else equal, typically a larger sample size will allow us to get more precise point estimates, and it will narrow down the margin of error. The general formula that we use for coming up with an interval estimate for a point estimator is first to calculate the point estimate, and then we both add and subtract a margin of error. So it is possible to provide an interval estimate for many different types of point estimators. So what we'll do is we will fill in this equation the point estimate with something like the sample mean or something like the sample proportion, and then we'll both add and subtract a margin of error, and that margin of error will give us a range, a lower end and an upper end in a range that gives us an idea of how certain we are about the value of our point estimate. The wider that range, the less certain we are, and the narrower that range, the more certain we are about the accuracy of our point estimator as an estimate of the corresponding population parameter. So we're going to start out with a very simple case. We're going to talk about the interval estimate for the population mean. So you'll recall that our interval estimate is going to have to depend on drawing a sample and calculating a point estimator as our best guess of the population parameter. So we don't know mu now, but we can pull a sample of a given size, lowercase n, and from that sample we can calculate x bar, our point estimate. We just add up all the different values in the sample and divide by the sample size to get the average. That we know is an unbiased estimator of the population parameter mu. What we can also do, given our knowledge of the sampling distribution that we covered in the last chapter, is we can make sort of a probability statement around this point estimate x bar by calculating an appropriate margin of error. To some degree, the margin of error is a matter of choice, as you'll see in the next slide. So before we get into the mechanics of the interval estimate for the mean and then eventually for the population proportion, let me talk a little bit about the case that we're studying here and how it differs from the last chapter. In the last chapter, I had assumed that the population standard deviation was known, and that allowed us to use the standard normal or the normal distribution. So we used the normal distribution in the last chapter. We had covered it in the previous chapter, and we didn't have to introduce any new distributions. In this chapter, I'm going to kind of cover the more realistic case. Usually we don't know very much about the population, and both the mean and the standard deviation of the population have to be estimated from sample data, typically from the same sample. So if we estimate the population standard deviation, right, if we have to estimate it, if we don't know what it is, then we'll estimate it, and that will be, if you recall, the sample point estimator of the population standard deviation is denoted with an S. If that's the case, we call it the case where the population standard deviation is unknown, and our interval estimate, I've given you a hint about this already, it will be based on the t distribution rather than being based on the normal distribution. So that's very important. So we're going to be looking at a new distribution here. And the dispersion of the t distribution basically depends on a parameter called the degrees of freedom. We've seen degrees of freedom before, and the degrees of freedom in this special case, we'll look at other applications of the t distribution later, but where this will be different. But for this application, the degrees of freedom for a t distribution will be equal to n minus 1. By n, I mean lowercase n, the sample size. So the sample size minus 1 will be the degrees of freedom that we deal with here. So what I will tell you is that the larger n, obviously, the larger the degrees of freedom. And then as the degrees of freedom grow, the t-distribution sort of converges to the standard, or to a normal distribution with less areas that are out in the tails. The tails of the t-distribution are a bit fatter than the tails of the normal distribution. But as n grows, it's going to converge to a normal distribution for us. So if the sample's really large, say with degrees of freedom, let's say greater than 100, then we can really use the standard normal distribution as an approximation to the t-distribution. But one thing that I want to make clear is that everything I've said above really depends on the population being having a normal distribution. So it says here that if the population is not normally distributed, right? If it's not normally distributed, then we're going to need to use the central limit theorem. We're going to appeal to the central limit theorem, and that central limit theorem is going to justify the use of the t-distribution. So if you have, say, 30 or 50 observations, and you're not sure that the population is normally distributed, then you can use the central limit theorem to justify using the t-distribution in the same way that we use the central limit theorem to justify using the normal distribution in the case where we knew the population standard deviation. So this case is a little bit more realistic. We don't know either the population mean, the population proportion, and we don't know the population standard deviation either, and each one of them have to be estimated. Ergo, we use the t-distribution. So here's just a nice graphic of how the t-distribution and the standard normal distribution are related to each other. This is a t-distribution here. It has 10 degrees of freedom. You can see that this distribution has fairly fat tails, like I said before. There's more area out in the tails of this distribution, and there's less at the mean here, which is 0, right? And as the degrees of freedom goes from 10 to 20, you can see that the area kind of leaves the tails, and it comes up here into this other t-distribution that has 20 degrees of freedom. And as we continue to increase the degrees of freedom, we converge to this standard normal distribution right here. So there's a good relationship here between the t-distribution and the normal distribution, and they're fairly similar to each other. So I want to give you a look at what the table looks like for a t-distribution, because the tabulation here, it looks a little bit different than what we saw with the z table. And the reason is we have this additional parameter that we have to worry about, which is the degrees of freedom. So the way these tables are typically constructed is that you look up the degrees of freedom in one of the columns, and then you look up the area that's in the upper tail in the other column. So what we have in the top row here that I'm circling, what we have there is we actually have the area in the upper tail. And it confuses students sometimes at first when they see this table, because this is exactly what was tabulated in the middle of the z table, and now it shows up, in this upper row, right? So I could pick, I could pick a value, a standardized sort of a t value. There's a t value, and what I actually have in this top row is I have the area that's in the upper tail. It's not the area that's in the lower tail like in a z table, but it's the area that's in the upper tail. So you just have to know what you're looking at, okay? And then this value of t, once we know the degrees of freedom, this value of t is found inside of the table here. Right? And it was really the z-score, not the t-score, that we were looking up in the standard normal distribution. And now here we are. We've got these values that used to be looked up in the outer row and column, the margins of the table, and we were looking for areas in the middle of the table. Now the areas show up in the top row of the table. The degrees of freedom show up in the first column of the table, and what we're looking for are the t-scores in the middle of the table. So it kind of turns everything around a little bit on you in terms of interpreting the table. So just keep that in mind. But for example, if this area that I had shaded here, if I wanted that to be equal to 5%, 0.05, then I would come to the table here and I would look up 5% of the area left in the upper tail. And I would also need to know the degrees of freedom. Let's say the degrees of freedom were equal to 60. Then I would look in the table and I would determine that the right value of t is 1.671. So t here would be equal, that would be equal to 1.671. And that's how you use the table. It's a little bit different. The other thing I would point out, just consistent with the slide that I showed you previously, is that when the degrees of freedom gets really, really large, here it says infinity, basically the values that you see in the t-table are standard normal z values, right? Because it converges to the standard normal distribution. So, if you were to go to a standard normal table and you were to look up 0.9 in the left margin, and along the top you looked up 0.06, and then you read to the middle of the table, so you were looking up the value associated with 1.96, what you would find is you would find an area that would be consistent with the 0.025. Okay. So again, here we've got the area that's represented in the table, that's in the top row of the table, and the area that you would find, I guess, in the z table, I guess that would be 0.975, right? Because the z table that we've been using shows you the area to the left of 1.96, not the area that's left in the upper tail. So I guess I should point that out also. So it would be the 1 minus the 0.025 that you would find, and that would be a 0.975. So now that we understand how to read the a t-table, we could talk about how you calculate the margin of error. We know how to calculate the mean. All we need to do is calculate the margin of error here. And once we've calculated it, we'll add it to x bar to get the upper end of the confidence interval, and we'll subtract it to get the lower end of the confidence interval. Okay, and basically, this looks a lot like the formula for, standardizing values. When we standardized values before, we had mu. We had a value minus mu, the mean, and we sort of divided it by the standard error. And now what we have, that was equal to sort of a standardized value. Now we're taking the standardized value, and we're kind of, in a sense, we're solving this for x again. And we need to go on both sides of our estimate. We need to go both below it and above it, which accounts for the fact that we're both adding and subtracting here. This will be clear when we work through an example. So in this formula, x bar is the sample mean, and 1 minus alpha is what we call the confidence coefficient. Now the confidence coefficient is up to you. You choose the confidence coefficient. Standard values for the confidence coefficient are alpha equal, or 1 minus alpha rather, equal to a 90% confidence interval, 95% confidence interval, 1 minus alpha equal to 95%, 0.95. Those are common, or a 99% is very common too. So 0.99 or a 99% confidence interval. Obviously, if we know 1 minus alpha, it's easy to figure out alpha. So if we have 1 minus alpha equal to a 90% confidence interval, then alpha is obviously going to be equal to 0.1. It's going to be 10% of the area that's left over outside of the confidence interval. We'll talk more about that in a second. If I've got a 95% confidence interval, then clearly alpha is equal to 0.05. 5% of the area is left outside of the confidence interval. And if I have a 99% confidence interval, it's 1% that's left outside of the confidence interval. Okay? But then what you'll notice is that when we construct the margin of error, we take alpha and we divide it by 2. Well, why is that the case? Well, I mean, that's the case because we have two different tails that we have to consider when we construct the confidence interval. So again, one of my really bad drawings, if we have, if we've got a confidence interval, and we've got a mean here, and we want to go on each side of it, we're going to go everything's supposed to be symmetric here, right? We're going to go the same distance to the right and to the left to construct either a 90, a 95, or a 99% confidence interval, and I'll be clear about the interpretation of what that means in a minute. But if we're going to construct that type of a confidence interval, we're going to have area that's left over in both tails. Okay, by convention, the area that's left over in both tails is what we call alpha. So if we were constructing a 90% confidence interval, we would have alpha equal to 0.1. There would be 10% of the area that's left in both tails, right? Because the distribution is symmetric, that means that there's 10% divided by 2, or 5% left in each tail. So alpha over 2 in that case would be equal to 0.05. And so, you know, if we were looking up the appropriate t-value in a t-table, then on the top row, we would be looking for an area that's left out in the right-hand tail of 5% if we were building a 90% confidence interval and our level of alpha was equal to 10%. So you have to keep that in mind. There's 1 minus alpha, and there's alpha over 2, and alpha over 2 is what we use to find t when we're building a confidence interval. Okay. All right, so S and N are things we've already defined, the sample standard deviation and the sample size. Now for our interpretation, before we jump in, let's do an interpretation of what these confidence intervals mean. What a 90%, let's use 90% for example, since I was talking about that on a previous slide. We could talk about 95%, 99%, those would be standard confidence intervals also. But let's talk about 1 minus alpha, our confidence interval, confidence level being equal to 0.9. So that alpha, in that case, is equal to 0.1, and alpha over 2 is equal to 0.05. So there's 5% of the area that's left over in each one of these tails. Okay, so here's mu, here's our mean. And we construct this confidence interval, and we say that it's a 90% confidence interval because 1 minus alpha is equal to 0.9, and there's 5% of the area left in each tail. What that means is that in a repeated sampling sense, if I go out and I keep collecting samples of this size, and I calculate a confidence interval using this technique, I'm going to capture the true mean 90% of the time. And I'll miss the true mean, right? I'll miss it 10% of the time. That's the interpretation of the confidence interval. That's how we think about the level of accuracy, right, associated with our point estimate of the mean. So, you know, what I'm saying is that if you look at this interval here, it doesn't include the mean. You can see that the mean is outside of this confidence interval. So I could collect the data, and I could get a 90% confidence interval, and maybe the true mean is not included in it, okay? Or I could go out and collect a different sample of data, and I do this over and over again, and one time I collect a sample of data, and I calculate the point estimate and the confidence interval, and this one does include the true mean. You can see the true mean is right here, and it intersects that confidence interval. A 90% confidence interval basically just means that if I follow this procedure 90% of the time, the confidence intervals that I construct are going to look like this confidence interval, the one that includes the mean, not the one that doesn't include the mean. Okay, so that, strictly speaking, is how you interpret the confidence interval. So now that we know all of the basic building blocks and how to interpret the confidence interval for the mean, let's go ahead and look at an example. A student reporter for a newspaper here is writing an article about the cost of off-campus housing. We have a pretty small sample of one-bedroom apartments. We've got 16 one-bedroom apartments, and they're all within half a mile of campus. In the sample, the mean is 750 per month, so that's going to be our point estimate of the population mean. That's our best guess at what to what the cost of off-campus housing is on average. And we have a sample standard deviation of $55. So that's the sample standard deviation of housing prices. It's not the standard error of the estimate or the standard error that's associated with the sampling distribution of the mean, right? That's just the standard deviation of the rents that we see in our sample of 16 one-bedroom apartments. So we've estimated the population standard deviation using the sample standard deviation. So this is the case of the population standard deviation unknown, because we've estimated the standard deviation from the sample data. This is the more realistic case. This is what you're going to run up against most of the time. in practice. So what we want is a 95% confidence interval, right, in order to estimate the mean rent per month. So what we want to do is we want to build this confidence interval such that, 95% of the time, if we were to follow this procedure, we would end up with a confidence interval that included the true population mean or average monthly rent for this off-campus housing. Now, in order to do this, we need to ourselves pick a level of confidence, right, the confidence interval. Now, this time, instead of using 90%, we're going to use 95%. So 1 minus alpha is equal to 95%. That implies that alpha equals 5% is the area that's left in both tails. So 5% divided by 2 is 0.025. That's 2.5% left in each tail. So alpha over 2 is going to be equal to 0.025. So we're going to need to look up on the table a t-value that's associated with 0.025% of the area left in the right-hand tail, okay? And then we're also going to need to know the degrees of freedom. Degrees of freedom here is pretty easy to figure out. We have 16 one-bedroom apartments, and I told you that the degrees of freedom in these examples will be equal to the sample size minus 1. So 16 minus 1 is 15. Keep all of that in mind, and we'll look up that value of t right now because it's an essential component to calculating the margin of error. So step by step here, right, as I said, the 95% confidence interval implies that alpha is equal to 5% and alpha over 2 is equal to 2.5%, 0.025. So we look up that area that's in the upper tail that shows up in the column here, right? Looking at the first row of the table, and then we look up the degrees of freedom. The degrees of freedom here for t 0.025 is we're going to base it on n minus 1 degrees of freedom. So our sample size is 16. 16 minus 1 is 15 degrees of freedom. So we look up 15 in the degrees of freedom column, and we find where the 0.025 and the 15 intersect each other right there. So this value of t that we need in order to construct our margin of error is equal to 2.131. Keep that in mind. Okay, the rest of this is pretty straightforward. We simply plug everything into the formula in the correct place. So x bar, we know, we've already calculated that at 750. That was given to us. And we need to add and subtract the margin of error. And that margin of error is based on the 2.131, which we calculated as the t-value from the previous table. Right? Because we have a 95% confidence interval, we needed t.025, and that's associated with 15 degrees of freedom. So we looked up the right number in the table. And then we multiply that by the sample estimate of the standard deviation for the population, which is 55. That information was given to us. And we have to divide that, of course, by the square root of n to get the standard error of the estimate, right? Because we're talking about the sampling distribution of x bar here under the case where the population standard deviation is unknown. So we just put all the things into the formula correctly, and we get 750 plus or minus 29.3. So 29.3 is my margin of error. So I can take 750 and I can subtract out 29.3 and come up with $720.70. So that's the lower end of my 95% confidence interval. And if I take 750 and I add the 29.3, I get 779.3, and that's the upper end of my confidence interval. So I'm 95% confident that the mean rent per month for population of a one-bedroom apartment within half a mile of campus is between $720.70 a month and $779.30 a month. So what I'd point out to you is that the wider the bigger the margin of error, the wider the spread between the lower end and the upper end of my confidence interval, and that implies I'm less confident about my point estimate. Holding everything else constant, okay, the big factor that's going to improve your precision and give you a tighter confidence interval is going to be a bigger sample size. So as I've mentioned several times already, bigger samples are always preferred to smaller samples, right? This is all assuming that the sample that we've selected is consistent with, simple random sampling if we have a finite population, or random sampling if we have an infinite population that we're sampling from. This is all assuming that we have good sampling methods. Okay, very quickly I'm going to walk you through the same exercise talking about the population proportion. Really, it's the same thing that we talked about before, but the formulas change around just a little bit in terms of calculating the margin of error. So if you can complete the exercise for a confidence interval for the sample mean and you understand the way that that's constructed, you can really calculate a confidence interval for just about any point estimate as long as you know how to calculate the margin of error and, of course, the point estimate correctly. So in this case, we're going to continue to assume that the standard error is unknown, or the true, in this case, it's the true population proportion that's unknown. And we're going to calculate a margin of error that's based on the standard error of the estimate. In other words, the standard deviation of the sampling distribution of the sample proportion. So we're going to use the standard normal distribution. Here we're going to use the normal distribution again because we've got NP greater than or equal to 5. We're going to assume that that's true, and that's going to be the case in the examples that we look at here. And n times 1 minus p is greater than or equal to 5. These are the same conditions that we imposed in the previous lecture as a justification for using the normal distribution as the limiting distribution of the binomial distribution. So here we go. Here's the interval estimate. Here's a formula for it. It's pretty simple. We calculate the sample proportion, that's p bar. Then we're going to use z alpha over 2. So we're going to use a z table this time. Or we can use a z table, but I'm actually going to use the t table because I already have it in the slides here. But we're going to need a z alpha over 2. That's going to be multiplied by the standard error here. Okay, the standard error of the estimate. And we need to estimate it this time. Before we knew p, but now we don't. We assume we don't know the population proportion. So our best guess of the population proportion p bar is what we plug into our formula for the standard error of the estimate. So we have p bar times 1 minus p bar divided by n. Okay, so note that the standard error here and in the previous example didn't include the finite sample. The finite population correction. So keep that in mind. If you need to use that finite population correction, then that would show up in the formula here as well. Okay, so sticking with the example that we have, though, once again we have 1 minus alpha as the confidence coefficient, the level of confidence. And again, it's standard to use either a 90%, a 95%, it's pretty common, and a 99% is pretty common. Those are pretty common confidence levels for building these types of interval estimates. So we're going to need a z here. Remember that the standard normal is the limiting distribution for the binomial distribution. So if we're going to assume that np is greater than 5 and n times 1 minus p is greater than 5, then we're going to have really a large enough sample that we're going to be able to move on to the standard normal distribution to pick a z-score rather than having to go to the t table to do so, since the limiting distribution of the t distribution is the z distribution anyway. So we're going to go to the z table, or we'll look up the z value on the t table. And then p bar, of course, is the sample proportion. So all we have to do is get all the right pieces and put them in the right places, and we get our interval estimate. So here's a picture of the normal approximation of a sampling distribution for p bar, and we have the standard error of the estimate here, right? P times 1 minus p over n. Okay, we have to estimate that, of course, in this particular case. So we need to plug in our p bars. So those will go in there in order to get the standard error of the estimate. We've got 1 minus alpha of all of the values which show up within the confidence interval. And then alpha over 2, that's left in both tails. So once we know alpha, we need to divide it by 2 when we start thinking about looking up z-scores. So keep that in mind. The interpretation of the confidence interval here is exactly the same as any other confidence interval. It means that in this case, let's say that we're looking at a 99% confidence interval, constructed from using this approach from a given sample size. If I think about this in terms of repeated sampling and undergoing this exercise over and over again, 90% of such constructed confidence intervals, 99% of such constructed confidence intervals will contain the true population proportion, and 1% will not, if this is constructed as a 99% confidence interval. Okay. And likewise for 95% or 90%, you could construct a 52% confidence interval if you would like to, but it's not as convenient because the different values of t or z aren't as conveniently tabulated. So here's a quick example. We've got a political science survey, and there's an election campaign, and we found out that 220 registered voters out of 500 who were surveyed favor a particular candidate, and we want to develop a 95% confidence interval estimate for the proportion of the population of registered voters total that favor this particular candidate. So we don't have all the information from the population, we just have hopefully a random sample, a good sample. And what we found out is that we have 220 out of 500 who say they favor the candidate. So we're going to try to build a confidence interval, and the confidence interval here, just before we jump into the table, the confidence interval here is going to be a 95% confidence interval. So 1 minus alpha is equal to 95%. That means that alpha is equal to 5%, right? Because 1 minus alpha and alpha must add up to 100%. So we've got alpha equal to 5%, but we have two tails to consider because we have an upper end to our confidence interval and a lower end to our confidence interval. So we need alpha over 2. We're going to be concerned with alpha over 2, and alpha over 2 is going to be 2.5% of 0.025. So keep that in mind. Okay. So here's our table, and this is the t-table. Well, we can go ahead and we can use it in order to find our z-score, because we have this last column which gives us z-scores for various areas that are left in the upper tail. So once we get down to degrees of freedom of infinity, we're talking about z-scores anyway. So I'll just use this table, and I said that alpha over 2 is equal to 2.5%, right? And essentially what we have here is infinite degrees of freedom. So the z-score that we're looking for here is going to be equal to 1.96. That's going to be critical for calculating our margin of error for a 95% confidence interval. Okay, so we know we want a 95% confidence interval, and the z-score that we need to calculate the margin of error is 1.96. So here's the actual calculation. P bar is calculated by taking the 220 who favor the candidate divided by the entire sample size. So 44% indicated they favored the candidate. So there's P bar. That's going to go into the formula 3 times, once here, and once again here, twice in the calculation of the margin of error, and of course it's our point estimate. Okay, also we just looked up on the previous table, based on the fact that we want a 95% confidence interval, that z alpha over 2 is equal to 1.96. Okay, so we're going to plug in the 1.96. That's going to get plugged in right here, and of course we're going to need the sample size of 500. We're going to put that into the formula right here. Now we have all the pieces that we need to construct the confidence interval. Here's our 95% confidence interval. Plugging all of the data in, doing these very simple calculations, either in Excel or on your calculator, or in Python or R or something like that, you'll come up with 0.44 plus or minus 0.0435. So the margin of error here is 4.35%. So it's how many people in the population favor this candidate? Well, 44% with a margin of error of 4.35%. And what that means is that if you take the 0.44% and you subtract the margin of error, it means that if we construct a 95% confidence interval, it could be the case that on the lower end, 39.65% of the registered voters support this candidate, and then on the upper end, right, it could be the case that 48.35% of the voters favor this candidate. Obviously, we're less certain the wider that margin of error and the bigger the distance between the low end and the high end of our confidence interval. One way, again, to improve the efficiency of our point estimator and to get a more accurate answer, holding everything else constant, would be, of course, to increase the sample size. Bigger samples would give us a tighter confidence interval, everything else held constant.